Welcome to KCC Diesel Online. My name is Jeff Rush, and this is DST 110H, Physics for Electricity. So today's lesson, we're going to be talking about the use of Watt's Law, how to solve for electrical power, discuss the concepts of electrical fields, magnetic lines of force, and explain how an electron magnet is formed. Put into your own words how voltage is induced into a conductor by movement through the magnetic field. It's really important, that put into your own words. You need to be able to define electricity. You need to, all the way through the diesel program, you will be required to put into layman's terms the concepts that we're learning. Over time, you'll develop that technical language. But as we start, learning the key terms, learning the vocabulary of diesel and diesel electrical is very important. We're going to continue to work on this. It'll be a theme all the way through your diesel career here at KCC, and then in your career as a diesel technician or an automotive technician. You're going to tell stories. You're going to write down technicians' comments, and you're going to have to do it for warranty and be very, very technical. You're going to have to do it so that your service manager can read it and understand it. Other technicians can read it and understand it, and then so a customer can read it and understand it. And so those are distinct audiences. So you're going to learn how to, tech it up, and make it very understandable for a technician, to make it very technical for a warranty administrator, or I won't say dumb it down, but make it relatable for a customer, something that they can understand, knowing that they don't have your technical knowledge. So when we're talking to customers, we drop the three-letter abbreviations. We can't say it's a mass, we can't say it's a MAP sensor. We have to say mass absolute pressure sensor. Manifold absolute pressure sensor, and so you have to, you really have to do that as you're going through. So that's something we'll build as we go along. We're going to describe how an indicator or capacitor stores energy, discuss how a negative voltage spike is generated when current flow through an inductor is ceased, and explain the similarities between a capacitor and an accumulator when used in the hydraulic system. We're going to talk about how force, work is force that results in movement, and we'll talk a little bit about how that works. We'll talk about the amount of force exerted times the distance traveled yields the amount of work performed. Power is the rate at which work is performed. In other words, instead of just the force required to move it, but now we're attaching it to a time, so that we can talk about power. That's what a horsepower measurement is really doing. And then electrical power measured in watts. So we'll talk about that. So here's Watt's Law. So in a previous lesson we talked about Ohm's Law and how that relates. And now we have Watt's Law, which is watts equals amps times volts. And we'll talk a little bit about that. And this is the equation, right? The pi equation. And that's really good, and we'll talk a little bit about how to relate that. 1 second here. Okay, so as you see here, I've put this into that familiar circle, kind of our Ohm's Law circle. And then, so watts is on top because that's, oftentimes what we're finding for. So watts is equal to amps times volts. Okay, so as we look at this, if we have one of these, we can find for the other. So let's say we want to cover up our V here, and so that would be what we were trying to find for. So if we want to find for our voltage and we know our watts and our amps, we're going to divide our watts by our amps. If we want to find, if we know our watts and our voltage and we're looking for amps, we can use this math the same way. We cover up the A, and what's left is the watts divided by volts. And then let's say we know the amps and the volts, then we can find for this. We can find for watts by multiplying amps times volts. Okay, so we'll get into that quite a bit in the lab portion of the class, but I just wanted to introduce the concept. All right, magnetism. So current flow produces magnetism. Magnetism can produce current flow. So there's that physics property for every action, there's an equal and opposite reaction. So if current flow produces magnetism, then magnetism can also produce current flow. And that's a pretty interesting concept, and we'll get into it a lot in our lessons going forward, because it becomes a very important part of our culture as we go through. We'll talk about it often, as you know, in regards to voltage and solenoids and all these different things, because it can produce kind of a ghost voltage that needs to be mitigated. So we talk about that pretty often. All right, so every magnet has two distinct poles, north and south. I think most of us have probably played with magnets, and you know that if you bring them together, they're they repel each other, and if you flip it over, then they suck to each other. That's a pretty important distinction to make. All right, so here's what the magnetic lines of force look like. So if you took a bar magnet and some iron ferrite or some iron filings, you would see this reaction here. Kind of like when we used to play. I don't know if any of you guys ever did it. They had the little guy with the hair, and the iron filings was the hair. You can make mustaches and beards. That kind of same thing. That's exactly what we're doing with this. All right. So here we have a little compass, and we're going to do this demonstration in our lab, and you'll see that the magnetic lines of force line up with the south and north pole, but in opposite, because of the way the magnetic lines of force and the magnetic flux field are lining up. All right. Opposite poles of a magnet attract each other. The attraction of unlike poles increases as they get closer to each other. Like poles of a magnet repel each other. The repulsion of those like poles increases as they get closer to one another. So you can actually break a magnet by pushing them together. They'll actually snap. And then when they do, of course, things flip around and they try to find opposite poles to attract to. All right, so here's another kind of demonstration of that, the repelling. So these two are attracted to each other because they're opposites. These repel one another because they're similar or like. So we want to have that understanding, because we use this all the time in automotive with solenoids and different type of mechanisms. All right, so here we have the current flow and magnetism, and we have that right-hand rule of thumb. So this right-hand rule of thumb is just basically talking about current flow. So if we're talking about electrical current flowing from positive to negative, whichever way our thumb is facing, that's the direction of the arrows. Again, that's a physics property, and it's great. It's very good to know, but we're never really actually going to diagnose a magnetic field in that way. Not in automotive and diesel. It's just not something we do. It's great to know. It's a tad bit of physics trivia for you, but it's really not applicable. And you're going to find that can be true with electrical, physics. Some of it's absolutely applicable, so very important, and then at other times it's not. So we'll talk a little bit. I'll try to let you know what you need to be paying attention to and what you don't. All right, strength of a magnetic field surrounding a conductor is directly proportional to the current flow. So let's talk about this. So right here at the top, we have a 1 ampere current flow going through a wire, and when we take our compass and we put it next to the wire, it does nothing. There's not enough attraction to make it do anything. It's not enough to attract the needle. We haven't created a strong enough force. Now that same wire, we up that by 3 times to 3 amperes, and now our needle is attracted and it's trying to align itself with the wire. And we're going to do this experiment in the lab, so you'll get to see this. Now there is some application for this, because there are some old school tools out there where you're going to take a magnetic ammeter and stick it on the wire and actually be able to sense, and it's really kind of it's rudimentary, but it works. But you're going to sense how much current is running through that wire, which is good for shorts and all sorts of things. They use short finders and different things like that for figuring this out. All right, magnetic fields cancel out the space between conductors, causing the conductors to move closer. So magnetic fields cancel out, so as you see up here, and then as they close together. So with the current flow in the same direction, this causes the two to move towards each other, and then the conductors will move together. Basically, just because the current is flowing in the same direction, the magnetic lines of force are both in the same direction, right? So I mean, the thumbs are pointing towards you, and so they're gonna come together. But if I had one wire sending power this way and one wire sending power in the opposite direction, they're going to oppose each other. Now, why is this important? It really has to do with how you design a harness, how you look at how to build a harness. You don't want to put these wires together in close proximity if they're flowing lots of current, because there can be some bleed over. You can create induction into the other wire. So two conductors with a 10 amp current combine a 20 amp current. So again, we're inducing that current into one another. So you got to be very careful, right? If you put them together, they're gonna create more voltage. And you may not want to be supplying 10 amps, or you may want to only supply 10 amps to something, and then now when you're adding extra amperage, there's extra potential there for damaging a circuit, or just overpowering a wire, burning it up. All right, when current flows through a loop, the wire, the magnetic fields combine to form a single stronger magnetic field. So the smaller fields create a larger field, and basically those windings. That's how a generator works. We're taking the wire and wrapping it around and making bigger magnetic fields and making stronger voltage. All right, reluctance. Reluctance is the opposition to flow of magnetic lines of force. So when you think of reluctance, I just think of resistance, resistance to flow. So some materials such as nickel, iron, steel provide a path of less reluctance for magnets. So they're sort of reluctant friendly. So that's why you'll see iron cores in motors. That's, iron's cheaper than nickel, so that's why you're going to see iron and steel in there. Nickel's in there somewhere too, you know, especially in the metallurgy or the compounds that we use. But typically we use that steel and that iron. When current flows through a wire wrapped around an iron core, the magnetic lines of force will concentrate on the iron core and create a strong magnet known as an electromagnet. We will build an electromagnet down in the lab, so you will get to see that. It's a pretty interesting physics lesson. Some of us have already done it, and it'll just be review for you. Some of us have never played with an electromagnet, so we'll get to play with that. So why are electromagnets important in the industry? We use them all over. And our electromagnets, we really turn them into solenoids, and we produce work with them. So, you know, your door lock, an electromagnet. Your relays, for lack of, are an electromagnet. So lots of things like that we're using. And so we have to know the properties of an electromagnet and magnetism, because when magnetism builds and collapses, it creates a different phenomenon, and we have to be able to deal with that. All right, creating current flow with a magnet. If the conductor is passed through a magnetic field and it cuts the lines, so it's running. I'm sorry to figure out how to do this with my hand best. If the lines were running this way, and I think we have a pretty good diagram of this, so I'll quit trying to do it with my hands. If we're cutting back and forth through here, so we're actually cutting this way, and we're cutting the fields, we're going to produce voltage. Okay. If, however, we're going up and down through the lines, so we won't be cutting any fields. We won't be going through that magnetic field, so we won't produce any voltage. So it's got to be interrupting the fields. An inductor is a wire that is wound in series in a series of coils. Inductors have a core of ferrous metal. Inductors are rated in henries. Okay. Inductors store energy in the form of a magnetic field. An inductor will inhibit the initial flow of current, known as counter electromotive force, or CEMF. This is important because CEMF creates some issues, and then actually can be, we just have to understand that it's there and what it's going to do and affect. And we get into this with starter motors and things like that. So once current flow is interrupted in an inductor will try to maintain the flow. So current flow through an inductor. So let's look at this diagram here. Magnetic field no longer expanding. So we've overcome the counter EMF, and we've built a nice strong field here, right? And our current is flowing through this wire like so. Okay. When the magnetic field collapses back into the wire, or the field collapses, either because current flow is decreasing or is cut off completely, we are going to have a collapse. That collapse is going to create voltage. So Lenzs Law, the polarity of an induced voltage is such to oppose the charge in current that it produced. So there's Lenzs Law explained. So let's look at this circuit here. As we go through the circuit, we're going from positive to negative. So we come up, we go through the closed switch, we go through through this path here, and we come back. We also, because we're in parallel, we're going to come up, we're going to go through this resistor R2, back through L1, and back to ground. Okay, so we have two different things happening there. Now, when we open the switch, we're going to see a phenomenon here. We're going to see something happen. Now, here we had gone through, so we had created a magnetic field in L1 right here. And so it was built up, it was charged, we'd overcome the counter EMF, we'd done all of that. Now, we've come back to ground. Well, now we've opened this, right? But there's an electrical charge being put out here. Now look how this happens. Up here with our inductor, our positive is at the top and our negative is at the bottom. But when we open this and the field collapses, it does it in a negative way. It flips the poles, if you will, and now our electricity is going to flow differently. Now, it's still positive, and positive is seeking negative, so it's going to try to find a path back to negative, so that potential difference. So it's going to come back up here, and it's going to go through our resistor 1, our resistor 2, and then come back, whatever's left in our voltage is going to come back to this negative again. And so that's important because that's how we manage voltage spikes in our system. That's how we manage that collapsing field, and so we'll talk about that because this is important. We do this in relays, we do this with diodes, we do this in many different ways, but we have to manage those voltage spikes from our electromagnets that we use in our vehicles. All right, inductor suppressed by a parallel resistor, and then this is exactly what we looked at in this. That's what we're basically doing in this circuit, is we're suppressing that voltage spike. We're managing it. So the inductor is suppressed by a parallel resistor. So the original current flow is interrupted, right? So we were going through this way. Now this is a parallel circuit. So we had voltage flowing this way through and down, and we had voltage flowing this way through and down. And now we've interrupted the current flow. So now this electromagnet, this inductor here, its field's going to collapse, and we need to manage that. We cannot have that because now it's going to want to feed back up here. So if this was our PCM or our powertrain control module or a body controller, we're going to have problems that could damage that circuit. So we want to just manage that, and one way to do that is just to add a resistor in here with the electromagnet, and then when that field collapses, it's going to do just like that last slide. It's going to flow through this resistor and back to itself rather than seeking ground up here, okay, or down here. So that's how we manage that current, okay. So transformers are used to step up a changing voltage. So one place that we see transformers used on a pretty regular basis is our alternator. Okay, we're alternating current. We're staying with the same voltage though, so we're trying to change the voltage in an alternator. So that may not be a good example. One place I like to see this is step-down transformers, where we're taking our 120 volt at the wall and we're running it through a transformer, and we're stepping down the output to 12 volts, like with your computer. Okay, so you'll see that's a step-down transformer. This is a step-up transformer. Where you're going to see something like this is in the automotive coil for your spark, so your secondary ignition coil. That is basically exactly what's happening there. Our input is 12 volts. Our output is much higher. We're talking about kilovolts. So we have so many windings on this side, and we have more windings on this side, and the magnetic force built up in here is inducing more and more voltage into this secondary. So you have your primary voltage coming in and your secondary spark and everything else going out. So that's exactly how a coil works. And here in our diagram, you'll see that. So what's happening here is we've got our negative, right? We're connected to the chassis. That's what this signifies right here, is that it's chassis ground. And so we have our positive. Now our positive potential is going to seek out a path to ground, right? So we're going to come up, we're going to go through the closed switch, and we're going to come down in here to the primary wires, okay? And the primary wires are going to look for ground. Well, in this case, our ground is provided by the ignition module. That ignition module is opening and closing the contacts, because remember, in order for this to happen, we have to saturate the coil. And so what we're going to do is we're going to create this field right here, and it's going to induce voltage into the secondary. But it's not really going to throw that off until we open that. Remember, it's the collapsing fields that create that phenomenon. So we're going to hold that, we're going to saturate the coil, we're going to overcome all that counter EMF, and we're just going to be a tightly wound bundle of electricity waiting for some place to go. Then when the ignition module opens, like it does right here, it's going to collapse that field, and that collapsed field is going to go into these windings. And these windings are much more. So again, remember, we're amplifying that voltage, and that voltage is going to go up through this wire, seeking ground, right? Well, the spark plug, the housing is ground, so this part here is ground, and the ceramic portion is insulating from the grounded portion, so the internal core of a spark plug is insulated. The outer part is grounded. So we're going to send that spark through to this tip here, to that metal tip, and that metal tip is then going to basically create a small lightning strike. Okay, but in order for it to jump that gap, that spark plug gap, it's actually got to be so many more, obviously more volts than 12. 12 volts isn't going to do that. So that's when we get into our 30,000 volts or 30 kilovolts, 15 kilovolts. So depending on the strength of your coil, that's what you're dealing with. And so it jumps that, and then basically your rotor or your electronic ignition is then now going to saturate the next coil, or saturate the same coil going to the next wire, and so or next wire and next spark plug. So again, we're not trying to talk about engine performance, but this is the application of those step up, step down resistors, or transformers rather. And so that's what you're trying to do, is you're trying to, hey, I've got 12 volts. How do I make more voltage so that I can have this spark over here? So using these windings was pretty ingenious. It was definitely a leap in technology. All right, capacitors. So we use capacitors in the same way. So capacitors are a storage device. Okay, capacitors are electrical devices used to store energy in the form of an electric field. Okay, so we're going to build a field inside this little capacitor. And capacitors consist of two metal plates spaced close together. A thin, non-conductive metal, a dielectric material, separates the plates. Okay, a dielectric has a very high resistance value. The metal plates of the capacitor are connected to the electrical circuit, and capacitors are rated in farads. So you'll see farads, you'll see microfarads. A farad is actually a very large measurement when it comes to capacitors, so we'll talk a little bit about that. All right, so capacitors store energy in an electric field. So here's our positive plate and our negative plate. So obviously, we're using the magnetic lines of force to create that field in turmoil. Okay, and as long as we have positive and negative going to that capacitor, it's going to store that energy until we have an event that releases it. Okay, so here's a capacitor in a circuit. So here we are. We have our switch closed, and we're going through our first resistor here. Then we're going across the capacitor. That voltage across the capacitor is increasing. Then we open the switch, okay, and now we're open, right? There's nowhere for this positive to go, right? And there's nowhere for this voltage to go. This capacitor is now just charged. It's just excited to be there, just looking for something to do, right? So as soon as it finds something to do, it's going to release that voltage and produce some work, some light, some heat, and so that's what we're going to see. So then when we close the capacitor, okay, now in this third position here, we've closed that capacitor. Now that capacitor is looking to do some work. So again, that capacitor is positive on this side, so it's going through the resistor, okay, basically flipping the poles and coming back to negative again, and it is going to produce work. So in this case, this resistor could be a heat resistor, could be could be a resistor just to perform some other task. It could be a light, could be a diode, could be a solenoid, could be lots of different things. And you're going to find out as we go through electrical hybrids, or using capacitors instead of batteries, and all sorts of crazy stuff. So capacitors are up-and-coming technology. The design of the capacitor, we have these mega capacitors now that can do some serious work. One more thing about capacitors before we move on. Capacitors are typically why when we unplug our TV, when we unplug our electronics, and you flip it over because, I don't know, your kid has, shoved some quarters in the VCR, or, done something dumb, or we have, and you go to tear that electronic piece apart, there's warning labels. Capacitors are oftentimes what it is, or why those warning labels exist, because that capacitor could be charged to a very high level of voltage, and can actually shock you and hurt you. And it's DC voltage, so it can do all sorts of damage to your muscles and body and whatnot. And so it's unexpected, because we think, oh, I unplugged it. Certainly, there's no battery in there that could hurt me, but this capacitor lives in there. And so we'll talk about that. Capacitors actually getting discharged hurts. It's a pretty good sting. I used to play with capacitors inside those disposable cameras. So how many of you guys have ever used one of those, and you hit the little flash button and you can hear the capacitor charging? It goes and it kind of charges the capacitor, and then the light comes on for the little flash. Well, when you take those disposable cameras to the 1 hour photo, which barely any 1 hour photos exist anymore, you tear that bad boy apart and there's a capacitor in there. And so we used to take them and throw them at each other, and someone would grab it, and they would inevitably make the contacts for the capacitor and shock themselves, or get shocked. And it was a lot of fun, but it also, like I said, hurt like the dickens. So, and if you're not expecting it, just the shock alone could cause you to have some other secondary accident. All right, well, let's talk about work. So work is an activity that involves force and movement in the direction of that force as described by the equation. So work is equal to force times distance. So, let's say, your boss asks you to move a box, okay? So this box is way too heavy for you. You can't pick it up, so you just push it. So you exert that force, and you push it over there. So you moved that box from point A to point B, and you produced some work. So work is measured in pound-feet. So, if that was a 60-pound box, you pushed that a certain distance. That's how much work you performed. Now, a 500-pound weight is lifted 1 foot. That equals 500 foot-pounds. So if that was a 500-pound weight and you pushed it and you moved it 1 foot, 500 foot-pounds of work. Energy. Okay, let's talk about energy. Energy is the capacity or ability to perform work. Okay, as we sit in the chair waiting for our boss to give us the orders, we have energy, right? We have that potential energy. We're ready. Energy is measured in pound-feet as well. So if I can move that 500-pound box 1 foot, that is, I have 550 foot-pounds of potential energy. Now, kinetic energy is the energy of motion, okay? So kinetic energy, something spinning that's able to do 500 foot-pounds of work, like a crankshaft, that's the kinetic energy. And then heat is a form of energy, right? So one of the properties of energy is that it never really goes away. It turns into light, heat, or motion. So you really can't disperse energy. It just changes form. So the McMuffin I ate this morning is being turned in, it had caloric value. I'm burning it up. I'm using it in heat. I'm using it in sound. So it had potential energy, and then it is expelled, right? So potential energy is energy that is stored and ready to perform some amount of work. So there's some really interesting ways to think of this, but try not to go to a dark place with this example, because I always have one that's kind of dark. But if you think about an example, how many of you have seen? How many of you have seen a? Sorry, I dropped my mic. Have seen a river flowing? Okay, that river obviously has a tremendous amount of energy, right? Water's flowing, right? So how do we harness that potential energy? Well, so we've done things like dammed up rivers and run turbines with the water, right? We harnessed the river's potential energy. Now, that energy, though, was more kinetic, right? It was moving energy, right? So when we dam up the river, now the river's not flowing, but the water rises, right? And so that water has, foot-pounds of energy, right? And we place our turbine down here, and the water comes down, and it pushes through our turbine, and that now produces the work. So we turned kinetic energy into potential energy, back into kinetic energy and electrical force, and we've changed the states of the energy being used. All right, power. So let's go back to our box that we were moving earlier. This 500-pound box we moved 1 foot. So power is the rate at which the work is done. So a really weak person might be able to move that 500-pound box 1 foot, but it might take them, an hour. A really strong person might be able to move that box 1 foot in a minute, or 60 seconds is a minute, 30 seconds. So power is often measured in watts or horsepower. Horsepower is a crazy measurement. It's really a weird way to relate to a power measurement, but we'll talk about that. 1 horsepower is defined as the amount of power necessary to lift 550 pounds at the rate of 1 foot per second. So let's put 50 pounds back more into our box, and let's say a really strong person could move that 550-pound box 1 foot in a second. Then that person would have 1 horsepower. And that 1 horsepower would be equal to 746 watts. So in America, we've always used horsepower as our power measurement. My car has this many horsepower, and we really like that horsepower measurement. We use it in lawnmowers, we use it in cars, we use it all over. Well, it's really a strange, arbitrary kind of number, and so watts is a little bit better in a sense. And so you're going to start to see diesel motors for sure measured in watts. We're starting to go to that metric system, which makes a lot more sense oftentimes. And instead of having to do this equation, so horsepower here is equal to torque times RPM divided by 5,252. So that 52 is just a number, just a conversion factor from the SI units of torque and angular velocity to torque measured in pound-feet of angular velocity measured in RPMs. It's like I said, it's a very crazy number to come up with. And so it makes sense to go to watts and all of that, but it's going to be a long time before the American public is going to say, oh, I have a 550 horsepower. No, I have 20,000 kilowatts, 20,000 watts, 20K horsepower. It's a weird number. It doesn't really roll off the tongue. I see why the horsepower thing is so ingrained in our culture, but going towards the metric system, eventually I think a lot of things like diesel motors and things like that will be measured in watts. All right. Kinetic energy is the energy of motion. The amount of kinetic energy depends on the velocity and mass of that object. The formula to determine kinetic energy is Ke equals one half times mass times velocity squared. And we'll talk a little bit about this in lab, not a lot. We may talk more about this during hydraulic term. We might talk about it during brake term, a little bit during engine term. But again, this is the physics of electricity. So really this is one time where we start to introduce the concepts of electricity into our lessons. And just the physics of automotive into our lessons. So, all right, forms of potential energy, gravitational potential energy. So we talked about this a little bit before, the gravity of that water when it's dammed. So the gravitational potential energy, the GPE, equals mass times acceleration due to gravity times height. So the mass of whatever it is, the acceleration due to the force of gravity pushing down on that, times the height of that object. So spring potential energy is another form of potential energy. And then you have chemical potential energy. An example of chemical potential energy is diesel fuel or gasoline. So obviously that's potential energy sitting there. It has caloric value. If we light it off, it's going to create energy. Heat, light, gas. So that chemical potential energy changes into a couple of different types of energy as it's changing, and then we have our reaction. Okay, I'm going to let you guys read through the summary and try to glean what you can from that. All right.